Okay, thank you. Thank you very much. I'll confess this is my first type of presentation such as this, but I was happy to be a part of this study. As was mentioned, I am a representative for Region 3 on the national mining team with EPA, and we've been talking for the last several years within that group about the potential for extracting critical rare earth elements from mining waste, both hard rock mining and coal. So this ROAR grant project seemed like the perfect equation. There we go. This is where the Shamokin watershed lies. The picture before was the acid mine drainage running through the town. I have a lot of pictures here because I think that tells part of the story. So as I became aware that the National Mining Team was looking for sources of critical minerals, I reached out to people that I've worked with for quite a few years, particularly Dan Quarry and Chuck Cravata. We all participate in the Schuylkill Action Network, and I was aware that they had done critical minerals sampling in the past. So I reached out to them and asked them about some of the data, and they were very helpful in developing this proposal. Okay, the ROAR program is through our Office of Research and Development, and essentially it helps us fill data gaps for leading scientific questions. As you all know, there's not a lot of information on critical rare earth elements in either hard rock mining or coal wastes. So this seemed like a perfect fit. They're not huge awards of money, but they were enough to do some sampling and follow up on some earlier data that USGS Cravata had collected in 1999. What are critical minerals? I think everybody has kind of touched on that. It includes a set of 17 chemical elements. They're the 15 lanthanids, as well as scandium and yttrium. They're considered critical because of their national strategic importance, and as we all know, the supply chains are very vulnerable to disruption. We don't have a lot of information, as I touched on sources in coal regions, especially in acid mine drainage waters and refuse materials. We know that critical minerals are associated with ore deposits, both hard rock and coal, and they can be in all types of coal products, fly ash, bottom ash, and refuse. This picture right here is at the bottom of Trevorton. This is actually a coal silt dam where the fines wash out into a ponded area, and they collect the fines, and I think they were selling them to Ukraine as a fuel source. I will mention anthracite coal was recently named in an executive order as an emergency fuel source. There's a list of the 17 rare earth elements. Okay, the Shamokin project. I'm going to step over here a little so I can, oh, it's right here. The project was to identify quantities of rare earth elements in acid mine drainage and coal refuse. We wanted to see if there was recoverable quantities of REEs that could be used to offset costs for both acid mine drainage treatment and reclamation of large areas such as the area surrounding Shamokin. We opted to evaluate the AMD data using USGS water quality model, which Chuck talked on, the FREAK AMD model, and using OSM's model for long-term treatment costs and operations and maintenance. We're still in the development phase of that with Tetra Tech. They're running those models now to give us the final results. We're also taking these resources and others and putting together a toolkit of resources that will be available for optimal REE extraction and treatment strategies. And we hope this could lead to guiding private, state, and federal partnerships to develop treatment plant and pump stations and other reclamation projects. We also want to develop best practices for the evaluation and treatment technologies for extraction of critical minerals, as there are not a lot of best practices yet established. We're all kind of finding this out together in the last few years. So phase one of the program was sampling of acid mine drainage from 5 of the largest discharges in the Shamokin Creek watershed. Tetra Tech helped us identify those, and we wanted to do the same ones that Chuck Cravata did as well. so we could do a comparison of that data. The work was performed in May of 2024. We shared the preliminary acid mine drainage results with the community in December of 2024. Data indicated that 15 rare earth elements were present in the acid mine drainage and associated wet sediments. We did collect those where the iron was precipitating out. We collected those sediments and analyzed those as well. Phase 2 was to take a look at the large coal refuse areas surrounding Shamokin. Initially, we proposed to do cone and quarter sampling because we envisioned with such large refuse areas, I think the Trevorton alone is estimated to have somewhere between 17 and 23 million tons of material. So we wanted to do a sampling that was representative of the area, but it's kind of like looking for a needle in a haystack when you have that quantity of coal and you can't dig down into 300 or 400 feet of the material necessarily and get a sample, which was one of our constraints. So in the field, we actually walked the area extensively. We looked for drainage ways, major drainage patterns, or also oxidation reduction zones that we could see within the coal. And we tried to focus our sampling there because the goal of this was to try to identify quantities of. And I think all of us would agree there's plenty of room for follow-up sampling of these areas because I'm not sure that we hit all the hot spots or, have an accurate estimate of the total amount that might be present. For example, at Trevorton, Department of Energy joined us on this effort, and we sampled, DOE took a sample at the base pond at Trevorton, and I think the pH was around 3, they told me, and the total REE content was close to a part per million dissolved in acid mine drainage, so that's pretty good. We did use a field XRF to scan areas of refuse. Wherever we got positive hits, we took samples from there. We did secure landowner permission, and I want to thank SCRA. They were really helpful in Bucknell University and getting those permissions, as well as Dan Corey, getting that all worked out. We're awaiting our refuse results, but I do have some results from Penn State here. We split the samples with Department of Energy, Penn State. We still have some extra aliquot. EPCAMR was kind enough to help us out with getting some containers to store our refuse samples in, so I thank them as well. And most importantly, all of these refuse and AMD results will be listed on a DOE database for coal mining and coal wastes. So it will be used in comparison data throughout the country. This is the sample naming key, but it also shows the community of Trevorton and the Trevorton pile, which kind of looms over the town. This is a summary of the acid mine drainage wet sediment sampling performed by Tetra Tech. You can kind of see the sampling locations within the watershed. Since you're all familiar with Shamokin, you know the water kind of runs north and west and out westward towards the West Branch of Susquehanna River. So in the initial AMD sampling field measurements, I want you to notice that the Big Mountain sample had a much lower pH than the other sample locations. Honestly, in some of the AMD sample locations, we weren't able to get close enough to the source, I think, in terms of the acidity. So a lot of these sites have had time for the iron to oxidize a little and start to precipitate out, and the pH was coming up. So, general data trends. The Big Mountain sample had the lowest pH and the highest concentrations of REEs, 47 to 48 micrograms per liter. This also had the highest concentrations of nickel and cobalt, which is often associated with dissolving pyrite. The AMD water samples ranged from about 4 to 52 micrograms per liter. The Henry, Clay, Sterling, and Cameron sites, the wet sediment samples had the highest metals and REE contents, so about 359 and 298 milligrams per kilogram. The total REE concentrations in wet sediment and solid samples was 47 to 359 milligrams per kilogram. This is a picture of the weir just below the Big Mountain AMD where it wells up. So you can see all that iron precipitating out that I mentioned. The data sets did include characterization results for AMD and associated sediment, and they were reported, let's see, they were collected both filtered and unfiltered field samples, so we did some comparison of that to look at potential partitioning of the critical minerals and suspended solids in AMD waters. I wanted to give you this website because this is DOE's website that contains information on coal-based sources. So Shamokin's database, I'm sure, will be included here along with a lot of other coal sources. So the water results, as I mentioned, you can see Big Mountain is quite a bit higher in REE content than the other sites. They were fairly closely aligned, but Big Mountain stands out. Again, I think we were closer to the source of the acidity as it was welling up from the deep mine pool. Sediment samples, you can see Henry, Clay, and Cameron are pretty close there. They're the top ones. But they're closely followed by several of the other sites. The lower ones were Big Mountain, of course, because a lot of that material was still in solution. So that's the total REEs. Big Mountain still by far had the most reported. This shows kind of the source where it wells up, and then there's a side pond I think they constructed there to kind of take that extra flow from the location. And I mentioned there were 15 REEs detected in the water, as well as cerium. And let's see, wet and dry solid phases were 230 to 266, or 18 to 21 milligrams per kilogram of cerium. The Penn State refuse sampling results. EPA hasn't completed our refuse sampling yet. They're still working on the final results. So I used today, thanks to Barbara Arnold, who ran the samples for us at Penn State. I used their sampling results to present to you today. Also, again, thanks to Dan Corey, Chuck Cravata, EPCAMR, and SCRA for their help in this project. So the samples of the refuse material were collected at Trevorton, Cameron, Excelsior, Big Mountain areas, and they were split with Pennsylvania DEP, DOE Nettle Labs, and Penn State. And DOE did join us. I should take a step back and mention that Region 3 joined EPA Region 4 in a memo of agreement with DOE Nettle Labs to share information on coal mining sites. I'm sure many of you are aware, Region 3 has more coal mining and abandoned coal mine sites than anywhere in the country. So it was just, it just made sense to join in that effort with DOE Nettle Labs. And that's how they became aware of the Shamokin area and joined us on this sampling effort. As I mentioned before, the water AMD data is being evaluated by Tetra Tech using USGS and OSM software. And we're still working on the development of a toolkit of resources. So I wanted to show some of these pictures. Here's a view of Big Mountain, again, the AMD refuse, and the top of the refuse pile overlooking the town of Shamokin. Most of our sampling at Big Mountain was collected at the top of the mountain because the lower area had been reworked so much and had so many burn areas and other stuff that we felt might cause interference. This is a close-up picture of us sampling on Big Mountain. We tried to get, as I mentioned before, in the drainage ways. This was a drainage way that had formed in the refuse material. We also scanned everything with an XRF. This was a siderite sample in the parting material that we found in the coal. The Big Mountain area seems to be a much bigger mix of refuse materials. So we took some of those refuse materials. DOE actually kept a couple of these samples to do some three-dimensional mapping to see if they could figure out weathering zones and secondary mineralization in some of these samples. So here are the Big Mountain refuse results. 207 to 278 parts per million, and whole rock plus yttrium ranged from 228 to 310. Treverton. You saw a picture of Treverton before. This is kind of an oxidation reduction zone that seems to be happening in the pile. What's interesting about this pile, where you see those little ATV tracks on that kind of black ridge there, that ridge is over 100 feet high, and below it is a pond that DOE sampled during our investigation. So we're up on the top of the pile, probably, I would say that pile's at least 350, 400 feet. And you can see these zones where the sulfur and other metals are weathering out of the coal. So we were very grateful that DOE brought in some consultants to do ground penetrating radar studies, because it does help educate where you might sample for critical minerals and where we might look, to quantify the piles. Even quantifying the amount of material there is difficult given the terrain. We don't know what the natural land base was under most of these areas, because a lot of these represent over 200 years of mining. So the Treverton results, we had up to 265 and 295 with yttrium parts per million. This is Cameron Glenburn refuse area. As you can see, the refuse is up all on the mountain above the town. And this is the AMD discharge. You can see by the time it reaches here, it wells up, goes, I don't know how many feet down the side of a highway, comes under the highway, and finally comes out at this point. And that was the closest sampling point we had. So you can see there's already a lot of iron oxidation and precipitation happening. So we've probably lost some critical minerals in that material. And that is shown in the wet sediments as well. The wet sediment samples had quite a bit of material in them. So the Cameron refuse results were 324 to 342 parts per million. The Excelsior refuse area, there's a refuse pile along the highway. There's some good pictures that were shown of that previously. And then to the north, you see the little pond area. Directly north of that is an old coal refuse area. And I was told by one of these people that joined us from SCRA that they think there's two different mine pools that well up in that impoundment. And then they mix, and then they go out to the left where it says Excelsior AMD, and that's where they discharge to a neighboring stream. So this is what they look like in the field. There is evidently, some mixing going from the first pool over to the second one. And this is up on the Excelsior refuse pile, and this kind of speaks to the difficulty in sampling this kind of material. This pile lays right along the highway, and it drops straight down. So we were kind of restricted to sampling on the top of the pile here in Excelsior, because it really wasn't a good way to get to the bottom of, traverse that pile to really take a deep look at it. So we were using the XRF to scan these areas where water was coming over the refuse embankment. So the Excelsior results were total REEs ranged up to 278, and with yttrium, 306 parts per million. So in looking at this summary of material, REEs and refuse, I want to point out from some recent presentations, I, as a member of the national mining team, I sit in on a lot of presentations for critical rare earth elements that DOE supports. And there was a recent one that was more southern-based. University of Texas gave the presentation. And some key takeaways from that presentation, when you look at these values, I want to tell you that median REE ranges in Appalachian ash, coal ash, were 431 milligrams per kilogram. In the Illinois basin, they were about 282 milligrams per kilogram. And in the Powder River Basin in Wyoming, they were 264. So I throw those out there for you to kind of have some comparison of these results. We do plan to go into DOE's database and do a more detailed comparison of these REEs to, other comparative samples in Pennsylvania and other areas. one point I want to make is, in this presentation I sat in, is it's easier to extract critical rare earths from acid mine drainage than coal ash. It's already acidified and in solution. And as they've covered in several talks here, by doing a precipitation process, slowly raising the pH, you can maximize removal of REEs, whereas when you're dealing with the fly ash, it's bound because it's been burnt and partially melted. So you have to break those bonds to get the REEs out of the fly ash, which is a little more difficult and more costly. Let's see. And there can be localized hotspots. I noted the Trevorton site and how much they found in solution at the base in one of those ponds. This presentation by the Southern States University of Texas in Austin used an example of Gibbons Creek, Texas, which is a site that they have been sampling, and they found over 2,860 parts per million REEs at that particular site. I think they plan to do more studies on why it concentrated in one area, and I think the Shamokin area is, definitely a site where more study could be done as to where critical minerals might be concentrating in these giant piles of refuse. And with that, I thank you.